Welcome to today's scientific lecture on one of the most fascinating phenomena in fluid dynamics, the elastic fluid paradox. We're going to explore how droplets can behave both as fluids and as elastic solids depending on the timescale of the forces acting on them. So what exactly is the elastic fluid paradox? This is a counterintuitive phenomenon where fluids, which we normally think of as deformable and unable to maintain their shape, can actually behave like elastic solids under certain conditions. In bulk, fluids flow and deform continuously. Pour water from a glass and it spreads out, fills containers, and flows downhill. This is the behavior we're all familiar with. However, under high-speed collisions, or when subjected to strong electric field stresses, these same fluids can behave like elastic solids. They bounce, oscillate, and resist deformation, rather than flowing or splashing. The most striking example is this. A water droplet, when miniaturized and subjected to rapid forces, can behave remarkably like a rubber ball. Instead of splashing on impact, it bounces. This is completely counterintuitive. So the key question we need to answer is, why does this happen? What physical principles govern this transition from fluid-like to solid-like behavior? The answer lies in two key factors: surface tension and the timescale of the applied forces. Let me explain each of these in detail. First, let's understand surface tension. Surface tension is the cohesive force that exists at the interface between a liquid and its surrounding medium, typically air. Imagine a droplet as shown here. The molecules at the surface experience a net inward force because they have fewer neighboring molecules on the outside compared to those in the bulk. This creates a tension that acts like an elastic membrane surrounding the droplet. We represent surface tension with the Greek letter gamma. For water at room temperature, gamma is about 72 millinewtons per meter. This means that if you were to create a 1-meter line on the water surface, the surface tension force pulling along that line would be 72 millinewtons. Now here's the crucial insight. Surface tension creates a pressure difference across the interface. This is described by the Young-Laplace equation. The Young-Laplace equation states that delta P, the pressure difference across the interface, equals gamma times the sum of 1 over R1 plus 1 over R2, where R1 and R2 are the principal radii of curvature. For a spherical droplet, both principal radii are equal to the radius r of the sphere, so the equation simplifies. Delta P equals 2 gamma over r. This is the Laplace pressure inside a spherical droplet. Notice that this pressure is inversely proportional to the radius. Let's do a numerical example to see how significant this pressure can be in small droplets. Consider a water droplet with a radius of 1 millimeter. That's r equals 10 to the negative 3 meters. Plugging into our equation, delta P equals 2 times 72 times 10 to the negative 3 divided by 10 to the negative 3, which gives us 144 pascals. That's about 0.14% of atmospheric pressure, not very significant. But now consider a much smaller droplet with radius 10 micrometers. That's r equals 10 to the negative 5 meters. Now delta P equals 2 times 72 times 10 to the negative 3 divided by 10 to the negative 5, which gives us 400 pascals. That's about 14% of atmospheric pressure, which is quite significant. At even smaller scales, say 1 micrometer radius, the Laplace pressure reaches 144 kilopascals, which is greater than atmospheric pressure. This internal pressure makes tiny droplets behave like pressurized elastic spheres. Now let's talk about the second crucial factor, timescales. The behavior of a droplet depends critically on how quickly forces are applied, compared to how quickly the droplet can respond by flowing. There's a characteristic timescale associated with surface tension called the capillary time. This is the time it takes for surface tension forces to restore a droplet to its equilibrium shape. The capillary time tau cap equals the square root of rho r cubed over gamma, where rho is the liquid density, r is the droplet radius, and gamma is surface tension. For water, the density rho is about 1,000 kilograms per cubic meter, and we already know gamma is 72 millinewtons per meter. For a 1 millimeter water droplet, tau cap is approximately the square root of 1,000 times 10 to the negative 9 divided by 0.072, which gives about 0.37 milliseconds. For a smaller droplet of 100 micrometers radius, the capillary time drops to about 37 microseconds. The smaller the droplet, the faster it can respond. Now here's where things get interesting. What happens during high-speed collisions? Let's think about a droplet hitting a solid surface. Imagine a droplet approaching a surface with velocity v. The collision happens over a very short timescale, which we call t-collision. The collision time is approximately r over v, where r is the droplet radius and v is the impact velocity. Here's the critical question. Is the collision time greater than or less than the capillary time? This determines whether the droplet behaves as a fluid or as an elastic solid. Case 1. If the collision is slow, meaning t-collision is much greater than tau cap, the droplet has plenty of time to flow and deform. It will spread out, possibly splash, and behave as a typical fluid. Case 2. If the collision is fast, meaning t-collision is much less than tau cap, the droplet doesn't have time to flow. Surface tension acts like an elastic restoring force, and the droplet bounces like a rubber ball. We can quantify this behavior using a dimensionless number called the Weber number. The Weber number compares inertial forces to surface tension forces. The Weber number W equals ρ v squared r divided by gamma. Ρ is density, v is velocity, r is radius, and gamma is surface tension. At low Weber numbers, surface tension dominates. The droplet acts like an elastic solid and bounces. This typically occurs when V is less than about 5 to 10. At high Weber numbers, inertial forces dominate. The droplet deforms extensively and splashes. This occurs when V is greater than about 30 to 50. In the intermediate range, you get complex behavior including partial bouncing, oscillations, and sometimes satellite droplet formation. Let's calculate the Weber number for a specific case. A 1 millimeter water droplet moving at 1 meter per second gives V equals 1,000 times 1 squared times 10 to the negative 3 divided by 0.072, which is about 14. This is in the transition regime. Now let's discuss another fascinating aspect of the elastic fluid paradox, the effects of electric fields on droplets. When a droplet is electrically charged or placed in an external electric field, it experiences electrostatic pressure. This pressure can compete with or enhance the effects of surface tension. The electrostatic pressure is given by P electric equals epsilon 0 E squared over 2, where epsilon 0 is the permittivity of free space and E is the electric field strength. Epsilon 0 is 8.85 times 10 to the negative 12 farads per meter. This is a fundamental constant. When the electrostatic pressure becomes comparable to the Laplace pressure, the droplet becomes unstable. It can oscillate, deform into unusual shapes, or even break apart into smaller droplets. The critical electric field for instability scales as E, critical proportional to the square root of gamma over epsilon 0r. Notice again the inverse dependence on radius. Smaller droplets require stronger fields to destabilize. For a 1 millimeter water droplet, the critical field is roughly 10 kilovolts per meter. For smaller droplets, this field strength increases significantly. When a droplet is perturbed, either by collision or by electric fields, it can oscillate in various modes. These oscillations are another manifestation of the elastic behavior. The simplest non-trivial oscillation mode is the mode 2 oscillation, where the droplet alternates between oblate and prolate ellipsoidal shapes, like this. The frequency of the n-th oscillation mode is given by omega n equals the square root of n times n minus 1 times n plus 2 times gamma, all divided by ρh(o)r cubed. For the mode 2 oscillation, n equals 2, so omega 2 equals the square root of 8 gamma over ρh(o)r cubed. Notice that omega 2 is approximately equal to 1 over tau cap, the capillary time we discussed earlier. This confirms that the capillary time is indeed the fundamental timescale for droplet dynamics. For a 1 millimeter water droplet, the mode 2 oscillation frequency is approximately 2.7 kHz. That's an audible frequency. You could actually hear these oscillations if they were loud enough. Let me give you some helpful analogies to better understand this elastic fluid paradox. Think of surface tension as a trampoline membrane. When you jump on a trampoline slowly, you sink into it. But when you jump quickly, It acts like a rigid surface and bounces you back. The droplet surface behaves similarly. Just like a trampoline, if the timescale of impact is faster than the material can respond by deforming, you get an elastic bounce rather than slow deformation. Another great analogy is silly putty. If you pull silly putty slowly, it flows like a viscous fluid. But if you yank it quickly, it snaps like a solid. The behavior depends entirely on the rate of deformation. Think about a water balloon. When you poke it gently, it deforms easily. But when you slap it hard, it feels almost solid for that brief instant. The water inside doesn't have time to flow, so the balloon resists deformation elastically. This elastic fluid paradox has profound implications across many fields. Let's explore some of them. In inkjet printing, tiny droplets of ink are ejected at high speeds. Understanding the elastic behavior ensures that droplets maintain their shape during flight and impact properly on paper without excessive splashing. In industrial spray coating and painting, the Weber number must be controlled to achieve the desired surface finish. Too much splashing creates a rough surface, while too much bouncing prevents proper adhesion. Raindrop impact causes soil erosion. Large raindrops can have high Weber numbers and cause significant soil particle displacement. Understanding droplet mechanics helps in developing erosion control strategies. In microfluidic devices, droplets are used to carry reagents and samples. At micron scales, surface tension dominates and droplets behave elastically. This enables precise manipulation using electric fields or acoustic waves. Let me pose a question. Why don't small droplets splash easily? Think about this for a moment before I give you the answer. The answer is that small droplets have very high Laplace pressure due to their small radius. This internal pressure makes them resist deformation. Additionally, the short collision time compared to the capillary time means surface tension acts as an effective elastic restoring force. Here's another interesting question. Can we make water droplets bounce on water? Is that even possible? The answer is yes. Under the right conditions, water droplets can indeed bounce on a water surface. This requires preventing the merging of the droplet with the bulk liquid. One approach is to use superhydrophobic surfaces. The water surface can trap a thin layer of air that acts as a cushion, allowing droplets to bounce multiple times before eventually merging. Another approach is to vibrate the water surface at high frequencies. The oscillations create a time-averaged repulsive force that can levitate and bounce droplets. This is known as Faraday wave levitation. Now let's discuss an advanced concept. What happens when viscosity becomes important? We've mostly ignored viscosity so far, but it plays a crucial role in very small droplets, or very viscous fluids. The Ohnesorge number O equals mu over the square root of rho gamma r, where mu is the dynamic viscosity. This dimensionless number compares viscous forces to the product of inertial and surface tension forces. At low Ohnesorge numbers, inertia dominates, and droplets oscillate freely with little damping. Water droplets have O around 0.001 to 0.01, so they oscillate readily. At high Ohnesorge numbers, viscosity dominates. Droplet oscillations are heavily damped, and the elastic behavior is suppressed. Honey droplets have O around 1 to 10, so they barely oscillate. Let's analyze the energy budget of a bouncing droplet to understand energy conversion during collision. Before impact, the droplet has kinetic energy, Ke equals 1/2 mv squared, where m is the droplet mass and v is its velocity. During impact, this kinetic energy is converted into surface energy as the droplet deforms. The surface area increases, which requires energy due to surface tension. The surface energy is E surface equals gamma times delta A, where delta A is the change in surface area during deformation. For a complete elastic bounce, all this energy must be recoverable. If the surface energy exceeds the initial kinetic energy, the droplet cannot fully bounce and will stick or splash. The condition for bouncing is approximately 1/2 rho v squared r cubed less than or approximately equal to gamma r squared. Simplifying, we get v squared less than or approximately equal to gamma over rho r. The maximum velocity for bouncing scales is Vmax proportional to the square root of gamma over rho dr. For smaller droplets, the maximum bouncing velocity actually increases. Let's return to electrical effects and see how we can manipulate droplets using electric fields in practical applications. Electrowetting is a technique where applying a voltage changes the contact angle of a droplet on a surface. This allows precise control of droplet shape and movement. Dielectrophoresis uses non-uniform electric fields to create forces on droplets. This enables sorting and manipulation of droplets based on their dielectric properties. Electrospinning uses very strong electric fields to overcome surface tension completely, creating thin jets that solidify into fibers. This is widely used to produce nanofibrous materials. Let me give you a fascinating real-world example: droplets in thunderstorms. Inside storm clouds, droplets experience strong electric fields and high-speed collisions. Electric fields in thunderclouds can reach up to 100 kilovolts per meter. This is strong enough to deform droplets and cause electrical breakdown of air, leading to lightning. Droplets in updrafts and downdrafts collide at speeds of several meters per second. These high-speed collisions can cause bouncing, rather than coalescence, affecting raindrop size distribution. The interplay between elastic bouncing and coalescence affects precipitation efficiency. Understanding this helps improve weather prediction and climate models. Let's look at an extreme case: superfluid helium droplets. These are among the most fascinating examples of the elastic fluid paradox. Helium-4 below 2.17 Kelvin becomes a superfluid, meaning it has zero viscosity. Droplets of superfluid helium have extremely interesting properties. The surface tension of superfluid helium is about 0.35 millinewtons per meter, much lower than water, but still significant at small scales. Superfluid helium droplets exhibit quantum mechanical effects. Their oscillation modes are quantized, and they can support persistent currents around their surface. Let me summarize the key concepts we've covered in this lecture on the elastic fluid paradox. First, surface tension creates an internal Laplace pressure that scales inversely with droplet radius. Smaller droplets have higher internal pressure. Second, the capillary time tau cap sets the fundamental timescale for droplet response to perturbations. It scales as the square root of r cubed. Third, when the collision time is much shorter than the capillary time, droplets behave like elastic solids and bounce rather than splash. Fourth, the Weber number quantifies the transition between elastic bouncing and fluid splashing behavior. Low Weber numbers mean elastic behavior. Fifth, electric fields provide an additional control parameter that can dramatically alter droplet behavior through electrostatic pressure. Sixth, viscosity, quantified by the Ohnesorge number, damps droplet oscillations and can suppress elastic behavior in very viscous fluids. Finally, understanding the elastic fluid paradox has applications ranging from inkjet printing to atmospheric science, from microfluidics to materials processing. The elastic fluid paradox beautifully illustrates how the behavior of matter depends critically on the time scale and length scale at which we observe it. A droplet is not simply a fluid or a solid, it is both, depending on how we interact with it. This teaches us that scale matters profoundly in physics. What seems obvious at human scales can be completely different at microscales. Water that flows freely from your faucet becomes bouncy and elastic when miniaturized. Thank you for joining me in this scientific exploration of the elastic fluid paradox. I hope this lecture has given you a deeper appreciation for the subtle and fascinating physics of everyday fluids.